Hello and welcome to this episode of Climate 201. Now this episode is going to be a little bit nerdier and perhaps wonkier than normal, so I hope you'll forgive me for it, but I think it will provide an interesting insight into some broader issues in the field of climate change in a nice analytical way. So let's start with some figures. In 1750, human activities very roughly resulted in approximately 10 million tonnes of carbon dioxide a year being emitted into the atmosphere. By 2017, there were 37 billion tonnes of CO2 being emitted a year, a factor of 3,700 more. In 1750, the world population was perhaps 700 million. By 2017, it was around 7 billion, 10 times more. GDP, as we always have to say, is a flawed economic measure, but it does very roughly tell you the overall volume of activity in the economy, even if that activity is not necessarily good. When GDP was originally invented by Kuznets, he actually wanted to distinguish good and societally beneficial activities from all activities, such that there were penalties for negative activities. But then, during the Second World War, Keynes got involved and said that the easier to calculate metric of GDP should be used instead. That's by the by. I mean, one thing we should point out is that GDP was not invented properly until 1934. It's certainly not always been around that people have talked about growing the economy with the single-minded fixation that we now have with it. But there were plenty of estimates that have been published that attempted to now project this figure back in time and work out things like, okay, what was the GDP of the Roman Empire? What was the GDP of the Chinese Han Empire and all this kind of thing? Using these estimates then, we can see that the global GDP was perhaps $800 billion in 1750 and rose to over $100 trillion by 2017. In other words, the global economy is perhaps 120 times bigger today in terms of raw activity than it was in 1750. Since 1750, humans have come up with more and more uses for energy. It's worth pointing out that energy consumption can be described in different ways. Primary energy means the embodied energy in all of the fuels and inputs to a system, while final energy is the energy that's actually used. So, for example, if I burn a lump of coal in a power plant, converting around a third of its energy to electricity, the eventual use of that energy to, say, power a light bulb will only be a third of the primary energy consumption. So in that case, the primary energy takes into account this coal that's being input to the system, and the final energy takes into account the actual end use of that energy. According to Václav Smil, in 1800, humanity in total used around 5,600 terawatt-hours of primary energy every year. Back then, this was mostly in the form of what were called traditional biofuels, i.e. this is just people burning wood to heat their homes or to power rudimentary devices. And it was fairly static across the years, as this demand was pretty constant. That was 1800 then. But by 2018, this had grown to 157,000 terawatt-hours of primary energy consumption, from a whole range of different sources, including predominantly fossil fuels, but also nuclear, wind, solar and hydropower. In other words, the primary energy consumption has grown by a factor of about 28 times between roughly 1750 and today. So when we compare the civilization that we have now to the one we had in 1750, we can see population is 10 times bigger, CO2 emissions are 3,700 times bigger, GDP is 120 times bigger, and the primary energy consumption is about 28 times bigger. So what's the point of telling you all this? The point is that there are several different things that can drive changes in CO2 emissions from an individual society or a civilization as a whole. And it's important to be able to disaggregate them to determine what's driving changes in emissions. For example, between 1750 and 2018, population grows by a factor of 10, economy by 120, energy use by 28, and all of these things have tended to happen together, and that means that our CO2 emissions have grown by a factor of 3,700. GDP growth is driven by population growth. More people means more economic activity, and also more demand for energy. But of course, it also is driven by other things. So for example, even if the population stays constant, it could be that you're doing more economic activity with those people, or they're demanding more energy on average. So the question arises, if you're emitting CO2, is it because the population has increased? Because the population is wealthier and therefore demanding more products which require more CO2 to be made to increase? Because your economy is using more energy? Or because the means that you're using to generate energy have become, on average, dirtier or more polluting? This is the purpose of the so-called Kaya decomposition, or Kaya identity, developed by Japanese economist Yuichi Kaya in 1997. Essentially, this tries to, heuristically, for the sake of education, split up CO2 emissions into the drivers of these emissions. So the CO2 emissions of a country, or even a planet, can be expressed as the following. CO2 emissions equals CO2 per unit energy, multiplied by energy per unit GDP, multiplied by GDP per person, multiplied by the number of people you have. So we start with the CO2 per unit energy. That's a measure of how polluting our procedures are to generate energy, the carbon intensity of energy, you can call this. Then we multiply by energy per unit GDP. In other words, how energy intensive is our economy? How much energy are we consuming to generate the GDP that we have? Then we multiply by GDP per person. How much GDP does each person have? A sort of rough guide to how wealthy the economy is once you account for population. And then finally, we multiply by the population. Looking at things in this way allows us to start to analyse what's driving changing CO2 emissions. And it also illustrates part of why the baseline is for emissions to continue to accelerate in their growth. The OECD recently suggested that global GDP per head would rise 2.6% a year, every year on average, until 2060. The world's population will continue to grow by 1 to 2% a year until the middle of the century, according to many analysts. With these long-term trends then, you can see that even if CO2 per unit energy and energy per unit GDP remain constant, these trends are going to push emissions higher, even if we don't grow hungrier for energy or choose to burn more fossil fuels to produce that energy. The baseline would be that emissions would rise. If the economy and the population continue to grow, then we need to get cleaner in terms of our energy production, or more energy efficient in terms of our economy, or both, every year just to tread water and to keep emissions the same. So one of the advantages of expressing CO2 emissions in this way is we can start to analyse what any change in CO2 emissions is down to. For example, we can look at one of the most dramatic collapses in CO2 emissions in history, which was from the former Soviet Union. Famously, the CO2 emissions from the Soviet Union countries fell dramatically as the USSR collapsed. They fell by around 35% in these countries between 1990 and 2010, even while emissions across the world in general rose by 44%. So we can now ask, was this due to people moving away from these countries? Was it due to these countries becoming cleaner in their economy? Did they start producing energy more cleanly? Did they shift from economies that used a lot of fossil fuels? Was it due to economic collapse in these countries instead? And what fraction of this change is down to each of these factors? Now, when you do this decomposition, although it shifts from country to country, it's clear that the overall driving factor is a big economic recession associated with the collapse of the Soviet Union, which caused large drops in CO2 emissions. There's a paper, Drivers of CO2 Emissions in the Former Soviet Union, a country-level IPAT analysis from 1990 to 2010, which looks at this in much more detail using the IPAT analysis, which is similar to this Kaya idea of decomposing the change in CO2 emissions into all of these different factors that influence it. Now this finds that CO2 emissions fell by around 48% between 1991 and 2000 in the former Soviet Union. Now the changes to the energy mix and carbon intensity are quite small, around 4% each, and the economy actually becomes more energy intensive, using more energy per unit GDP, by about 8%. The population over that time is pretty static, so we can see that a huge fraction of this decline in CO2 emissions was caused by the approximately 40% decline in the economy over this decade. Let's apply this to another example, my favourite, the home country of the UK. The UK has widely been touted as one of the world's leaders on climate change due to its record on greenhouse gas emissions. And indeed, since 1990, the UK's CO2 emissions has fallen from about 600 million tonnes of CO2 a year in 1990 to around 370 million tonnes of CO2 a year in 2018, a decline of about 38%. So now we want to question, okay, how's this being driven? Is the UK's economy slowing down? Is it that the economy depends less on energy production now? For example, as we've shifted from manufacturing to a services economy, or as energy efficiency measures have been installed. Or maybe it's due to the renewables that we're deploying and the switch to our energy being made in a less CO2 intensive way. Now, always to be acknowledged in climate geopolitics is that if economies gradually evolve from high-intensity manufacturing to services economies that import goods from overseas, as we've largely seen in Europe and the US, which used to be factories of the world and are now increasingly importing things from overseas, then there's a lot of unfairness in us asking developing nations to simultaneously manufacture all of our goods and also to reduce their CO2 emissions rapidly, having already made ourselves rich in part with the unconstrained burning of fossil fuels. Looking at the specifics of the UK between 1990 and 2018, we can see that the UK GDP has increased from 1.1 trillion to 2.85 trillion in 2018, although even in 2018 it was still lower than at its peak in 2007, so this is not a monotonic increase across that whole time. So according to this measure, the economy is about 2.5 times bigger. In terms of the energy intensity of GDP, a sort of combined measure of how efficiently energy is used and how much of the wealth production of a country depends on energy use, we see that the UK has declined from around 0.125 kilos of oil equivalent, a measure of primary energy use, per dollar of GDP in 1990, to around 0.062 kilos of oil equivalent per dollar of GDP in 2018. In other words, our demand for energy per unit GDP has more than halved in these years. Finally, we can look at CO2 emissions per unit of primary energy consumption in the UK, a metric of how well we are removing CO2 emissions from our systems for providing energy in electricity, transport, industry and agriculture. And this has fallen, according to my calculations from statistics provided by Enerdata, where you can look into this for your own country. That's ENER data. We've shifted from 2.68 kilograms of CO2 emissions per kilogram of oil used equivalent to 2.05 kilograms of CO2 emissions per kilogram of oil used equivalent, i.e. this has fallen by about 24%. So let's return to that headline figure then. We've seen that the UK's CO2 emissions have fallen by about 38%. We know that the economy has grown, and we know that it has started using less energy per unit GDP, and that it has also started producing less CO2 per unit energy. So the economy has grown quite a bit since 1990, but the effect of this has been offset by a more energy efficient economy, which is in turn due to energy efficiency, but also an economy that focuses more on services and not energy intensive industrial manufacturing processes. Meanwhile, the UK's energy production has decarbonised slightly, driven by a shift to wind power and natural gas and away from coal in the electricity sector, which has contributed, and this has been about a quarter of a reduction in terms of the CO2 per unit energy that we're using. So you can see that Britain's decline in CO2 emissions is driven both by our changing economy and also by slightly cleaner energy production than we had in 1990. It's about 24% cleaner now than it was then. So you can of course repeat this kind of case study for all sorts of different nations and different time periods to try and understand what the primary drivers of CO2 emissions are in the world. Enner Outlook from Enerdata, which you can access at enneroutlook.enerdata.net, is a fun example of this. Typically globally, what we've seen in recent years is that primarily economic growth and growth in energy demand has offset any deployment of clean technologies or shifts towards energy efficiency. The main force pushing emissions down has been economies using less energy than they did once to produce the same dollars of GDP. Now this is basically efficiency changes, even though as the economy has grown, overall energy demand has increased substantially since 2000. The CO2 emissions per energy use has only gradually begun to decline, and in 2015 is still higher than it was in 2000. So this has actually not yet been a major contributor to any slowing of emissions growth. So if you look at this for the world as a whole, there's a graph from the Global Carbon Project, which I will put up on Twitter at PhysicsPod, and you can see how this has changed. So you can actually see that there's a graph that I'll put up on Twitter at PhysicsPod, which actually shows that relative to the year 2000, the energy per unit GDP has fallen by about 20%. So that's sort of 20% more efficient at producing GDP from energy than we were before. The CO2 per energy has risen fractionally by maybe 5%. So really, in terms of the energy that we're producing, it's not actually any cleaner now in 2016 when this was drawn up than it was in 2000. The energy production, the demand for energy in total, has risen by about 40%, and the GDP of the world has risen by about 80% since 2000. So you can see that there's these factors: our increasing demand for energy and our increasing demand for GDP, global economic growth, have more than cancelled out the very, very slow, if at all, changes to the CO2 per unit energy intensity, and the sort of increasing efficiency of our economies in terms of using less energy to have more GDP. And that's been the story of global carbon emissions from the year 2000 to 2015, 2016. So over the last couple of decades, basically. So looking at the implications of this kind of decomposition, we can obviously see what we might ideally want to happen. If we assume that we are ruthless economists who always want to maximise GDP and economic growth, which is an assumption we'll come back to later, then we really want to reduce the CO2 per energy by deploying more renewables and more carbon neutral alternatives to existing fuels. And we want to reduce the energy per GDP by making our economies more energy efficient and less dependent on processes that require large consumption of energy to produce this value that we're trying to maximise. Now, these are obviously going to be much easier and better, arguably, and also less controversial than trying to shrink the economy or the population. People often talk about population as a solution to climate change, but obviously to actually reduce the population by any meaningful amount, you would need to kill or avoid the birth of billions of people, which seems like a rather dramatic thing to do when you could achieve similar percentage reductions in the world's CO2 emissions with a push to install renewables, to drive more energy efficient cars, or to phase out coal. Similarly, realistically speaking, given that a global reduction of GDP by just 0.03% in a year, 2009, was referred to as the Great Recession and the global financial crisis, you can see that we can't intentionally pull too hard on the GDP lever without radical changes in how the world is run, given that the world is currently addicted to endless GDP growth. Now, the problem here is that although you may want to make these radical changes to how the world is run, given that it's addicted to endless GDP growth, and I may well agree with you there, it's likely that if we want to get emissions to net zero, we might want to have to focus on something else. And thankfully, I would argue, it's probably much easier to become more energy efficient and decarbonise our supply of energy than it is to convince the world to cut its GDP in half. But if we accept that our best levers to pull on are energy efficiency and CO2 efficiency of energy production, and we want GDP and population to be able to continue to grow, or at least not shrink too much, then we have to accept that we have to reduce these things fast enough to overcome any growth in the economy or population that is going on at the same time if we actually want to reduce emissions. The aim, then, is to decouple economic growth from increased use of fossil fuels and increased greenhouse gas emissions. And that's really reversing the broad sweep of human history in nations across the world, where until very recently, the increased use of fossil fuels has driven a lot of economic growth. Luckily, we have a set of cheaper and cleaner alternatives. But the point here is that there's a very real risk that the world, in trying to balance economic growth and our obligation to cut emissions and stop climate change, acts far too slowly and lets the stalemate carry on, as we've seen in recent decades, where clean technologies are deployed far too slowly to overcome this economic growth. And this leads to a lot of the criticisms of the Kaya decomposition as it is. Because when you have this Kaya decomposition, you're centering things like GDP, and you can argue, quite rightly I think, that our focus is being put in the wrong place when you do that. Because obviously, the Kaya identity is just one way of decomposing things. We are simply choosing to break down the processes that lead to emissions in this way to reveal these drivers, but we could have chosen something else. We have tried to choose quantities like economic growth, population, energy consumption, and the emissions when energy is used that we reasonably expect to be drivers of changes to CO2. But we could have picked some other set of factors. Maybe a better decomposition would be to focus on something harder to measure but more fundamental. Human happiness, the progress of human society, etc. Something more aligned with our values than raw, brutal economic growth which misses out on a lot of subtlety. Then we would be rewarding ourselves for producing happier societies with less use of CO2, as opposed to larger economies with less emissions of CO2. And there's an argument that this would be substantially better. There are plenty who would argue that the whole effort to drive down CO2 emissions at the rate we need to would be much easier if we were willing to contemplate GDP standing still, or even declining degrowth, and not to prioritise the growth of the economy at all costs. I have a lot of sympathy for this view, but given we're in the econometric world here of Kaya identities and decompositions, and I'm presenting kind of quite a mainstream view of the problem. I'm going to save analysis of that for another episode. Now, there's another aspect of criticism for this kind of Kaya decomposition approach to looking at these things, which is the four drivers here aren't necessarily independent of each other. So predominantly service-based economies with a lower energy intensity of GDP also have higher GDP per capita, and this could be because of the different prices in the world economy between goods and services. Now again, you can argue that maybe our world economy overvalues services and undervalues physical goods, but that doesn't really matter when that's something that's sort of not included in the Kaya identity here. And naturally, there are aspects that are concealed within each driver which can make it difficult to see what's causing the driver to change. So take, for example, the energy intensity of GDP. It could be that a society's overall energy use is declining as its economy changes. It could be that energy efficiency measures are leading to less wasted energy. Or it could simply be that some sectors of the economy are growing more quickly than others. So imagine that you're in an economy where, say, the financial sector is growing much, much faster than manufacturing. Then, even though you might still be emitting the same amount of CO2, technically burning the same amount of fossil fuel, your energy intensity of GDP will go down because there's more people in offices working out how to trade Bitcoin with each other than there are people smelting things in factories. So the drivers of the drivers are of course concealed by this simple Kaya decomposition. You can't determine which sectors are the largest contributors to the emissions, for example. So if you were to take, say, a classic example, the transport industry, the personal transport industry in the West, then you might see that CO2 emissions from this are actually rising or staying constant, and it wouldn't necessarily be clear to you why that is. And in fact, what's happening is that while some cars are getting more energy efficient, consumer preferences are driven towards more and more bigger SUVs and trucks, in part because they make more profit for the companies that sell them. And this is meaning that although it may be that the number of passenger miles is fairly constant, the actual fuel consumption is higher than it was before. Now, you also can't necessarily extrapolate trends in a Kaya decomposition. For example, the UK's 38% decline in CO2 emissions has been largely driven by a decline in the power generation sector, as we switch from coal to wind and natural gas. In fact, Britain recently, as I record this, celebrated something like 100 days without burning any coal, but it was actually stopped by the heat wave that we just had here. It is an immense irony, because the heat wave was hot enough that a lot of natural gas plants couldn't operate and the coal plants needed to operate instead. I think it's a real direct irony of climate change that we've had to start burning coal because of an unnaturally warm heat wave for Britain, but that's sort of by the by. Now, analysis by Carbon Brief has suggested that around a third of the decline in UK CO2 emissions was due to a cleaner system for generating electricity. A third was reduced fuel consumption by business and industries, so that's energy efficiency generally. And 20% was down to reduced electricity consumption and efficiency measures there. But only 7% was due to changes in the transport sector. So it's arguable that with the easy reductions in the electricity sector largely achieved by shifting away from coal to natural gas, which emits less CO2, the harder reductions in transport and agriculture remain. In other words, we can't simply extrapolate the CO2 intensity improvements in the UK into the future. You need to know where the CO2 intensity improvement is coming from, because it's certainly not uniform across all sectors of the economy. Now, some of this type of thinking has been important in terms of climate geopolitics too. So in the Paris Agreement, which most of the countries of the world have signed up to, every party determines its own target called an NDC. Not all of these NDCs, these nationally determined contributions, are specified specifically in terms of emissions cuts. For example, India's target is to reduce the carbon intensity of its GDP by a third by 2030. In other words, with an economy growing as quickly as India's, its actual emissions could easily be higher in 2030 and still meet this pledge. But since its economy would be decoupling from fossil fuels and its growth would be decoupling from fossil fuels, it still counts as progress in decarbonising. And you can argue that, especially for developing countries, this is a slightly more equitable way of dividing up responsibilities than insisting that every country should cut its emissions. Finally, in our analysis here, I'd want to point you to one paper that was quite interesting that came out recently, called Less than 2 degrees Celsius of Warming by 2100 Unlikely, which you can read for free online. Essentially, this paper looks at the countries of the world through a Kaya decomposition like the one we talked about today, analysing trends in energy efficiency, GDP, population and carbon intensity, etc., to try and determine what might happen if current trends continue unabated. So this is something like an attempt to construct a climate change scenario, but just assuming that current trends go on as they are at the moment. What they find is that, in general, GDP per capita is expected to climb by 1.8% a year, while carbon intensity declines by 1.9% a year. In other words, if current trends continue, these effects can be expected to cancel each other out for the next few decades, leading to emissions that either flatline or only rise slowly throughout the century. This, of course, would lead us to blast through the 2 degrees Celsius Paris target, which requires emissions to start falling rapidly, pretty much now, and leads, according to the authors, to an average temperature increase of 3.2 degrees Celsius by the end of the century. They do this with some Bayesian modelling to try and estimate various different possibilities, so there's actually a probability range of temperatures depending on current trends. But in other words, the message from this kind of decomposition is really the same message that you'll hear from lots of other analyses of global CO2 emissions. To get to anything like the Paris Agreement goal of 2 degrees Celsius, business as usual is not going to be enough. We need some pretty radical changes, and we need rapidly accelerating decarbonisation compared to the trends of the last few decades. And it has to come from somewhere. It has to be either we abandon our model of economic growth, or we find out a way to make our model of economic growth compatible with CO2 emissions by reducing the CO2 emissions per unit energy we produce, or we find ways to create value that we want, things we want, without using as much energy. So, as complicated as the situation might sound sometimes, it's really very simple. Your choices are slash your economy, might be unpopular, slash your population, even less popular, particularly with the people who you're slashing, slash the amount of energy you use to produce your economy, okay, energy efficiency, that's one way you can go, and slash the CO2 emissions per your unit use of energy, cleaning up your act when it comes to producing energy. And that's as simple as it gets. So I'd like to thank you for listening to this rather technocratic episode of Climate 201, where we've talked about Kaya decompositions, Kaya identities, and tried to analyse some of the drivers of CO2 emissions and how economists and social scientists think about them in individual countries. It's a very oversimplified analysis of a very complicated problem, much like the use of GDP is itself. But once you get there, you can start to ask some of the more pertinent questions about where CO2 emissions are coming from, what's causing them, and how they might change in the future. Thank you for listening to this episode of Climate 201. You can find us on the web at physicspodcast.com. You can follow us on Twitter at physicspod. If you have any comments, questions, concerns, things you want to know about climate change, things you want to hear about, now is the time to ask them. You can, on the website, there's a contact form that you can send me messages. I will try and respond to everything. And if it's a good enough question, I'll respond with a whole episode. Or there may be one coming down the pipe that deals with your particular question. Until next time, then, please take care.